Hi, this is Ipek Ozai. I'm a sophomore industrial engineering student at Bahçeşehir University. Today, with my dear friends Cenk Erarslan, Emercan Aslan, and Ahmet Utku İnce, we're going to present our term project for this semester for our class, Manufacturing Processes. Before starting to present, I would like to thank to our dear teacher, Alper Cemci, for this amazing semester for teaching us in this class. So, what have we decided to manufacture? What did we choose to focus on manufacturing for this project? We have decided to manufacture universal joints in this project, and let's dive into more in this process. Let's see how are we going to produce this, how much does it cost, which materials are used, which requirements are there, all that stuff. So let's continue with me, and then you'll see my other friends. They will also present. Firstly, let's state our design goal and let's focus on that. Our design goal is to reach high quality and cost-effective production line integration. Regarding to the mechanical functionality, our design allows continuous torque transfers across angles. It ensures high kinematic efficiency with low friction. And for the mechanical ergonomics, we ensure for interchangeability between yokes and spider crosses. Furthermore, bearing cups utilize interference fits under the ISO 87 standard. If we look at the application scope, which is an integral and essential part for automotive drivelines, this image here highlights the positioning of the universal joints in car bodies. Also, this little thingy, this little braid solution is also critical in aerospace and various other industrial sectors. Shortly, we can say that it plays a vital role in transmitting power smoothly across the different systems. In this slide, we see that we have two main tolerance requirements. The first one is axial alignments. Regarding to our first tolerance requirements, which is axial alignment, our maximum allowable axial alignment must remain below 0.02 millimeters, as you can both see from the figure, and it is written there with orange. Also, this current measurement shows a successful alignment of 0.01 millimeters. And our second requirement is vibration mitigation. And as you can see in the picture below, this picture shows us that precision fit maintains low vibration amplitudes.
Looking at the bill of materials in the table, our components split between in-house production and purchase parts. The core structural parts like the yoke keys are made from high-strength alloy steels, and the Spider Cross utilizes K-hardening steel for durability. And the four bearing cups are also produced in-house using low-carbon steel. And regarding the material selection, firstly for the input and output yoke keys, we chose AISI 4140 chromium molybdenum steel. Since the yoke keys face high torsional loads, this alloy provides excellent hardenability. By using hot forging instead of casting, we align the internal grain flow, eliminating microscopic voids and increasing the fatigue life. And for the Spider Cross, the most stressed component, we selected AISI 8620 case hardening steel. It combines an extremely wear-resistant surface with a highly ductile core to absorb sudden impact loads. And finally, the bearing cups are made of low-carbon AISI 1010 steel, chosen for its excellent cold formability and cost-effective machining. Now, let us examine how these materials are shaped in the hot forging stage. And for the initial shaping of our Yokeys and Spider Cross, we implemented a precise hot forging process. We utilize a massive 1600 ton capacity crank-type mechanical forging press. And before forging, the raw steel billets are heated in our induction heating system to temperatures between 1150 and 1200. This is well above the material's recrystallization temperature and reducing its yield strength to ensure maximum plastic deformation without cracking. The forging is done in a two-stage die sequence. Firstly, the preform stage optimizes the initial volume and followed by the final forge geometry to establish net shape features. This structural optimization aligns the grain flow, boosting the fatigue life by compared to cast alternatives. And lastly, flash removal is performed using a 200-ton trimming press while the temperature remains above for optimal edge quality. Once the raw forge geometry is achieved, we transition to precision CNC machining to satisfy critical assembly tolerances. For the input and output Yokeys, we use a CNC vertical machining center equipped with custom hydraulic fixtures to eliminate vibration. In Operation 1, we precisely turn the shaft section and mill the keyway. And in Operation 2, the Yokey ear holes are drilled and rimmed to a strict H7 ISO tolerance to ensure a flawless press fit with the bearing cups. For the Spider Cross, all four arms are machined in a single setup on indexed CNC lattice. This guarantees absolute axial alignment. We leave a grinding allowance to correct any heat treatment distortion. And additionally, we drill a lubrication channel through the core. And moreover, to give our AISI 8620 Spider Cross its final strength, we use a 3-step gas carburizing process as shown in the slide. First, in the carburizing step, we heat the part at 930 degrees Celsius for 4 hours. Carbon enters the surface, creating a hard outer layer. Secondly, we perform quenching. We quickly drop the hot part into a 60 degrees Celsius oil bath. This sudden cooling makes the outer layer extremely hard, while the inside core remains tough and flexible. Third, and lastly, we perform tempering at 180 degrees Celsius for 2 hours. This relieves internal stresses and stops the surface from being too brittle. This gives us a strong part with a wear-resistant surface and a shock-absorbing core.
And then we'll continue with line balancing and efficiency. So here we focus on our system performance evaluation. Our analysis highlights 3 major achievements. At first, we have no chronic bottlenecks. And then second, we maintain balanced workloads across the line. And finally, our demand target is met perfectly. From now on, I'll continue, and at first I want to talk about precision grinding and finishing. On this slide, CNC cylindrical grinding is used to achieve an H6 tolerance and a surface finish under 0.4 micrometers. This extreme precision is vital for driveline stability at 4,500 RPM. It prevents descriptive vibrations. Ultimately, it ensures a perfect mechanical fit, reducing friction and extending the assembly surface life. And now I'll continue with process routing and standard times. We start with input and output yoke. At first, it is hot forging, and then we'll continue with heat treatment, and at last, we'll finish it with CNC machining. And when it comes to spider crows, again we start with hot forging, and then it continues with CNC machining, and then case hardening, and at last precision grinding. And when it comes to auxiliary and assembly, we start with bearing cup, and then we finish it with final assembly line. Next, looking at the assembly line design, as you can see from the table, our process is structured across sequential stages. At first, we begin with subassembly and preparation parts, which takes a time of 26 seconds, and then we continue with input group assembly. It takes a duration of 28 seconds, which is followed by the output group and circlip. It takes a time of 27 seconds, and then here comes the finalization and QC, which takes 25 seconds of duration. Moving on to the U-shaped cellular plant layout, our facility is organized into main operational zones. First, we have logistics and storage, which directly feeds the raw material and handles finished goods. Second is the hot forging cell, which is structurally isolated for heavy industrial tasks. At third, the material flows into machining and heat treatment for final shaping. And then fourth, the parts enter the clean room assembly for pressurized precision fitting. And finally, all of this is governed by strict operational safety to separate industrial hazards from precision zones.
And now, moving on to the quality control and testing standards. As you can see, our comprehensive quality system is carefully built on these main categories. First of all, we utilize non-destructive testing in order to thoroughly scan the forged blanks. Secondly, we conduct continuous in-process inspection to closely monitor both tool wear and required tolerances. Thirdly, we make sure to fully evaluate the overall mechanical performance. And fourth, as our final step in this process, we perform dynamic balancing. Now, if we look at the statistical process control shown in the image here, you can see that we carefully monitor our critical feature by utilizing two main charts. First and foremost, we analyze the X-bar chart, which effectively tracks the overall process mean. And secondly, we move on to the evaluate R chart, which specifically monitors and process range, or in other words, the variability. And here is the economic analysis and conclusion. Our fixed costs are $310,000, with a variable cost of $22 per unit. Selling at $47, we make a solid profit at $25 per unit. This brings our annual break-even quantity to 12,400 units. Remarkably, we hit this target on just the 13th working day of production. Before we conclude our presentation, I would like to briefly share the key reference and the academic sources that form the foundation of our study. Thank you for listening us. Thank you for time and attention.